Welcome! Today, we're going to solve a classic system of equations that combines a sphere and a plane. Our goal is to find the points, x, y, z, that satisfy both equations simultaneously. In other words, we're looking for the intersection of these two surfaces in three-dimensional space. To get started, we'll use a substitution method to combine these two equations. Let's begin by isolating a variable from the second equation. Our first step is to rearrange the linear equation. Let's take the second equation, x plus y plus z equals 3. We can easily solve this for z by subtracting x and y from both sides. This gives us z equals 3 minus x minus y. This is a very important relationship. The next step is to substitute this expression for z into our first equation, the equation of the sphere. This will eliminate z from the first equation, leaving us with an equation involving only x and y. So, we take our original sphere equation, x squared plus y squared plus z squared equals 6, and replace the z term. We substitute 3 minus x minus y in for z. This substitution is the key to simplifying the problem. Now, we need to expand and simplify this equation. Let's focus on the squared term, 3 minus x minus y squared. We can expand this by multiplying 3 minus x minus y by itself. Let's distribute each term. 3 times the expression gives 9 minus 3x minus 3y. Then, negative x times the expression gives negative 3x plus x squared plus xy. And negative y times the expression gives negative 3y plus xy plus y squared. After expanding, we get 9 3x minus 3y minus 3x plus x squared plus xy minus 3y plus xy plus y squared. Let's collect the like terms. X squared, y squared, the two xy terms, the x terms, the y terms, and the constant. This simplifies to x squared plus y squared plus 2xy minus 6x minus 6y plus 9. This is the expanded form of our squared term. Now that we have the expanded term, let's substitute it back into our main equation. Remember, our equation was x squared plus y squared plus 3 minus x minus y squared equals 6. We replace the squared term with its expansion. Notice the repetition of x squared plus y squared. We have one pair from the original equation and another from the expansion. So, we can combine those. X squared plus x squared is 2x squared, and y squared plus y squared is 2y squared. This gives us 2x squared plus 2y squared plus 2xy minus 6x minus 6y plus 9 equals 6. We're almost there. The last step in simplifying is to get rid of the constant on the right side. We can subtract 6 from both sides of the equation. Subtracting 6 from 9 gives us 3. This quadratic equation in x and y represents the projection of the intersection circle onto the xy plane. It's a key result we'll use to find x and y. Solving this new quadratic equation, 2x squared plus 2y squared plus 2xy minus 6x minus 6y plus 3 equals 0 is tricky. It's a rotated ellipse. However, there's a geometric shortcut that can help us. Let's think about the intersection of a sphere and a plane. The intersection will always form a circle. Any circle has a unique center. For a circle formed by the intersection of a sphere and a plane, its center is the closest point on the plane to the center of the sphere. The equation of our sphere is x squared plus y squared plus z squared equals 6. This is a standard sphere centered at the origin, 0, 0, 0. So, our task is to find the point P1, P2, P3 on the plane x plus y plus z equals 3, that is closest to the origin. Finding the center point will simplify our problem immensely, as the circle's properties will be symmetric around it. There are several ways to find the closest point on a plane to a point not on the plane. One powerful method is using vector projections. First, we can read the normal vector to the plane from its equation. The coefficients of x, y, and z give us the normal vector. Our plane is x plus y plus z equals 3. So the normal vector is n equals the vector less than 1, 1, 1. This vector is perpendicular to the plane. The shortest vector from the origin to the plane must be parallel to this normal vector n. Let the closest point be P. The vector OP is the projection of any vector from the origin to a point in the plane onto the normal vector. We can choose the point 3, 0, 0 in the plane, so the vector A is less than 3, 0, 0. The formula for projection is A dot n over n dot n times n. The dot product of A and n is 3. The dot product of n and n is 1 squared plus 1 squared plus 1 squared, which is 3. This gives us the vector less than 1, 1, 1, 1. This means the closest point, which is the center of our circle, is P equals 1, 1, 1. This point lies on our plane and is closest to the origin. Alternatively, there is a geometric argument that allows us to find the center with even less calculation. Because of the perfect symmetry of our sphere and plane equations, we can look for solutions where x, y, and z are equal. If we assume a solution exists where x equals y equals z, we can substitute this into the equation of the plane. X plus x equals 3, which means 3x equals 3, and therefore x equals 1. If x equals 1, then by our assumption, y must also be 1, and z must also be 1. So, we found the point 1, 1, 1. Let's quickly check if this point lies on the sphere. Is 1 squared plus 1 squared plus 1 squared equal to 6? No, it's 3. This is a very important point of confusion. This point, 1, 1, 1, is not on the sphere. It is the center of the circle of intersection. Let me emphasize this. The point, 1, 1, 1, is the center of the circle, but it is not a point of the circle itself. The circle is on the sphere, not on the plane, so the center of the circle is on the plane, not on the sphere. It's the point in the plane that's closest to the center of the sphere. We now know the center of our circle is C equals 1, 1, 1. To fully define a circle, we also need its radius. We can find the radius by using the Pythagorean theorem. Imagine a right triangle. The hypotenuse is the radius of the sphere, which is the distance from the sphere's center, the origin, to any point on the sphere, including a point on our circle. The radius of the sphere, capital R, is the square root of 6. One leg of the triangle is the radius of our circle, which we'll call lowercase r. The other leg is the distance, let's call it d, from the center of the sphere to the center of our circle. Using the distance formula, the distance d between the origin and our circle's center, 1, 1, 1, is the square root of 3. The Pythagorean theorem relates these three lengths. R squared plus d squared equals r squared. Substituting our values, we get r squared plus 3 equals 6. Solving for r squared, we find the radius of our circle is r equals the square root of 3. So, our intersection is a circle centered at 1, 1, 1 with a radius of the square root of 3. We're looking for the points x, y, z that lie on this circle. Since it's a circle, there are infinitely many points. If you are asked for the solution, you should state it as the equation of the plane and the equation of the sphere, along with the properties of their intersection. The solution is the set of all points, x, y, z, that satisfy both original equations. We have now fully described the solution as a circle in 3D space. The circle's center is 1, 1, 1. Its radius is the square root of 3, and it lies on the plane x plus y plus z equals 3. You could also parameterize this circle if you needed to generate the coordinates of individual points. This is a common next step in such problems. Let's summarize what we've accomplished. Our objective was to find the intersection of a sphere and a plane. First, we tried a direct algebraic substitution. This worked, but resulted in a complex equation of a rotated ellipse in 2 dimensions. To simplify, we switched to a more elegant geometric approach. We recognized that the intersection is a circle, and the center of that circle is the point on the plane closest to the center of the sphere. Using either a vector projection or a symmetry argument, we found the circle's center to be 1, 1, 1. Then, we used the sphere's radius and the distance from its center to our circle's center in the Pythagorean theorem to find the circle's radius. We concluded that the solution is a circle with a radius of the square root of 3, centered at 1, 1, 1, and lying on the plane x plus y plus z equals 3. This problem demonstrates how understanding the geometry of surfaces can often provide a more intuitive and efficient path to a solution than pure algebra.